I am a physicist and he was a mathematician, and I can comment with any competence whatever only about his contributions to physics. These were, I could say, of three kinds. Two of these are indirect, and one type of contributions is direct. First, he contributed to physics by the mathematics that he created. He created the theory of unbounded operators. He contributed very greatly to the theory of group representations in Hilbert space and to the theory of ergodic systems. He liked the encouragement of physics or of concrete thinking on mathematics. He always said that if mathematics is left to itself and has to develop out of itself, it becomes baroque and uninteresting, and his liking not only for physics but also for other branches of knowledge, in particular economics, was based on this circumstance. The second type of contributions which he made to physics was made simply by being a mathematician interested deeply in physics. He convinced us that rigorous thinking creates distinctions not present in our usual, more sloppy thinking as physicists. This type of contribution was not as evident during Johnny's lifetime as it became since. There is a large school now, a very important school of theoretical physics, the so-called school of axiomatic field theory, which is based just on the fact that distinctions which were entirely neglected by physicists, which are in a sense foreign to physicists, were pointed out by him and are now coming into great importance and may forward the theory to a much greater extent than I am sure even Johnny anticipated. The third type of contributions to physics which Neumann made is a direct one. He solved certain physical problems. I don't mean principally small physical problems, but one very big one. The statistical interpretation of quantum mechanics, the understanding of what the quantum mechanical equations mean, was achieved, strangely enough, a good deal after these equations became known and were known as mathematical entities. He wrote a book about it, first in German, then it was translated into English, and it is called The Mathematical Foundations of Quantum Mechanics. I would like to tell you a few anecdotes to illustrate the unusual speed of Janči's thinking. There was a puzzle in the 20s which became rather popular, and it dealt with two bicyclists cycling toward each other from the two ends of a 40-mile track. A swallow is supposed to fly off from the one cyclist toward the other and meet the other cyclist, return to the first one, then go back to the second one and cover shorter and shorter distances. Well, the problem is, what is the total distance of the swallow's flight? The speed of the bicyclist was 20 miles and the speed of the swallow is 50 miles per hour. One can arrive at the solution of the problem rather quickly by noting that the two bicyclists will take just 1 hour to meet, because they start at opposite ends of a 40-mile track and have a speed of 20 miles each. During an hour, naturally, the swallow flies 50 miles because it's 50 miles per hour. Well, few people see the solution of this puzzle, and Johnny didn't see it either when Max Born, himself a very well-known scientist, a physicist, told him the story. In spite of this, by the time that Born finished the story, Johnny was ready with the answer. He said, well, 50 miles, of course. Born was astounded, and he said, you are the first one of my scientist friends who saw the solution at once. Johnny said, well, I can't understand that. It is a simple infinite geometrical series. And by the time Born finished with the story, evidently he had summed up the length of the infinitely many distances traversed by the swallow.